Hello friends, in this lecture we will learn about movement generating function and its properties. So first of all, what is the definition of moment generating function? Moment generating function, short form MGF of any random variable x is defined as expectation of e raised to power tx for any real parameter t. So it is a simply expectation of e raised to power tx. If one knows about expectation, how to calculate expectation, then he can simply find the moment generating function by finding the expectation of e raised to power tx, where t has a variation from minus infinity to infinity, and expectation should be well defined and exist. As we know that there are two types of random variables. One is a discrete type and another is a continuous type. If it is a variable is a discrete type, then expectation will be found using the summation etx fx. If variable is a continuous type, then expectation will be found using the integral etx fx dx. So we have only these two formulas for calculating moment generating function. It is basically expectation of e raised to power tx. This is the main definition of moment generating function. Now in this video, we will learn about few properties of movement generating function. Property number one, movement generating function of mcxt is same as movement generating function of x, where ct is as a parameter. So we will solve both sides, left hand as right hand side. First of all, we will take left hand side. What is the definition of movement generating function? Expectation of e tx. So in the stead of x, here it is a cx. So we will write here cx. So it will become e raised to power tcx. Now take right hand side, moment generating function of xct. So it is e tx. So here t, instead of t we have a ct. So we will write ct here, and opening the bracket it will become like this. So both things are same. So this property is a simple thing. If you can easily make c inside the bracket, you can easily make c outside the bracket. Next property, effect of change of origin and scale on moment generating function. Here we have to check the effect. Let us take variable x. We have to change this variable x into new variable u by changing its origin and scale. So we have defined u is equal to x minus a upon h. This is a change of origin. This is for change of scale. Now our aim is to find its moment generating function of u, and we know definition, it is the expectation of e raised to power tu, because instead of x here it is a u. Now use the value of u from here, it becomes x minus a upon h. Now breaking this bracket into two parts like this, expectation tx upon h, expectation minus ta upon h. This is the constant part and this will become outside the bracket, and we will have only expectation of this one. Now in the previous property, we can say this is our t and this is our x. It is mxt. In this way, we have find the moment generating function by changing its origin and scale, and its new formula is like this. If we make u of this type, then its moment generating function reduces into this type. Okay. Now, if we take particular case, ex is equal to new mean and h is equal to take standard deviation sigma, what does this u becomes? U is equal to x minus nu upon sigma. Here a, instead of a we have to take e expectation ex, which is called mean. So formula will be reduced e raised to power minus nu upon sigma mxt upon sigma. Instead of a we have taken nu, and instead of h we have taken sigma, which is the standard variate. This is a special case for normal standard variate. Okay. Property number three, the moment genetic function of sum of number of independent random variables is equal to product of their respective moment genetic functions. Let us suppose we have independent random variables. We have to find the moment generating function of their sum. So we will start with the definition: moment generating function of x1 plus x2 plus x and so on. According to definition, it will be expectation of e raised to power tx. Now breaking this expression into like this, etx1 dot etx2 dot so on. Since variables are independent, so this expectation can be break into this part, because if x and y are two variables, suppose x and y are two variable independent, so we can easily write like this: expectation of x, expectation of, if two variables are independent, we can break them into product part. So what is this? This represent homogeneity function of x1. This represent homogeneity function of x2. This represent homogeneity function of xn. So sum of variables is product of their homogeneity functions. Very important property. Next one, property of uniqueness. It is also very important. It says that homogeneity function uniquely determines the distribution. This implies that corresponding to given probability distribution, there is only one homogeneity function. It means that a single probability distribution does not have two homogeneity functions. It is always determined by only one distribution function. If a distribution function is one, it has only one homogeneity function. Okay, if two distributions are same and their homogeneity functions are same, then x and y are of same quality. They are same identical distributed. Now we have a limitations. There are few limitations of this homogeneity function. If a random variable x may not have moments, although its homogeneity function exists, a random variable x can have moments, but some moments, yet homogeneity function does not generate the moments. It means if it has a moments, but homogeneity function is not useful to find this. And third one is if random variable x have all or some moments, but homogeneity function does not exist. So these are the properties about homogeneity functions. If you like my video, please subscribe my channel. Thank you very much.